So now we're going to go through some properties of the cross product. And in order to state these properties, we're going to need three vectors. So we call them u, v, and w, and they're all going to be three-dimensional vectors. And we need a scalar, which we'll call k. So the first two properties are actually going to give us a really nice feature of the cross product. So let me write the properties down first, and then we'll look at what they mean. So the first one says that the dot product of u with u cross v is equal to 0. And when I write 0 here, I don't mean the 0 vector, right? Because this is actually a dot product. It's a dot product of u with this vector here, whatever it ends up being. So a dot products always give you back numbers. So it makes sense to write 0 here, not the 0 vector. So we're talking about the real number 0. And the second property says that the dot product of v with u cross v is also equal to 0. Okay, and what this tells you actually is it tells you that u and v are both orthogonal to u cross v, right? If the dot product of u and u cross v is equal to 0, that means u is orthogonal to u cross v. And if the dot product of v and u cross v is equal to 0, well then that means that v is orthogonal to u cross v. So let's summarize that. So this is a really nice fact about the cross product, and it follows from properties 1 and 2 of this list. So u cross v is orthogonal to u, and we can also say that u cross v is orthogonal to v. That's a really nice feature of the cross product. If you take two vectors and you take their cross product, the result is going to be orthogonal to both of the two factors that you started with. Okay, so the third property gives us some information about the length of u cross v. And the way we phrase this property is we'll say that the norm of u cross v is equal to, well, and actually, in order to avoid writing square roots, you could write the property in this form, but what you'd end up having is you'd end up having a square root on the right-hand side. So it just turns out to be convenient to actually write the equation so that the left-hand side is actually the square of the norm of u cross v. But really what this relationship is giving you information about is the norm of u cross v. It's important to realize that. And on the right-hand side of this equation, we get the norm of u squared times the norm of v squared, right? And that's part of it. That's not quite correct as it currently stands. That's not the whole story. But the next thing, this is actually going to turn out to be true exactly when u and v are orthogonal. But if they're not orthogonal, then you end up having to subtract this extra term. You have to subtract the square of the dot product of u and v, which if u and v are not orthogonal, then this will be a non-zero term. So this is true in general. Okay, and there's no need to memorize this property, which is true for most properties, although I would say that the first two properties are worth memorizing in the sense that you should remember that this is true. This is something that you don't want to have to look up. You want to just note. You want to have this at the tip of your brain, right? Ready to recall at any moment that the cross product of u and v is going to be orthogonal to both u and v in general. But property 3 is not worth memorizing. You can always look it up if you need it. But what you should remember is that there is a property involving the norm of u cross v. There is an equation that tells you how to express the norm of u cross v in terms of the norm of u, the norm of v, and the dot product of u and v. The details you can always just look up. And properties 4 and 5, those are also going to be properties that are not actually ones that are worth memorizing. And we're going to write them down. We're going to make an observation about them, and then we're probably never going to use them again in this course. But it's good to have in your notes, and you can always look them up later if you need them. So the first one says the following. If I take the cross product of u, and then the second vector in this product is actually going to be itself a cross product. So we're going to take the cross product of u with the cross product of v and w. So what do you get if you do that? Well, this fourth property is going to tell us. You end up getting this is maybe a bit weird, but this is what you get. You end up getting the dot product of u and w multiplied onto the vector v. And then you can subtract the dot product of u and v multiplied onto the vector w. Okay, and we'll comment on that in just a moment, but first we're going to write down property 5, which says something about the cross product of u and v with the vector w. So first take the cross product of u and v. Whatever the result is, take the cross product of that vector with w. That's what this says on the left-hand side of this equation. And on the right-hand side, it starts off, the first term is the same. You get u dot w as a scalar multiplied onto the vector v. And now, but the second term is going to look a little bit different. You're going to subtract the dot product of v and w multiplied onto the vector u. Okay, well, it's actually worth noting something here. That these second terms are not the same, right? At least they're not the same in general. Turns out in very specific cases they might be the same, but in general these second terms are different. So what that means is that this cross product here and this cross product here are different. So that means if you want to take the cross product of 3 different vectors, you have to specify which ones you want to take the cross product of first. You can't just simply assume that they're going to be the same. That's what properties 4 and 5 are really saying. So in general, let me summarize that here. In general, the cross product of u with v cross w is not going to be the same as the cross product of u and v crossed with w. And before we finish this page, we'll actually be able to write down a specific example of that. But really, this observation, this is what really the reason I wanted to state properties 4 and 5, but we're not going to use them for much other than that. Okay, another way to phrase it, what I've said over here, the cross product is not associative, right? Matrix multiplication is associative, but for vector product or the cross product, it's not associative. Property 6 is going to actually tell you another property that basically it gives you another property that the cross product doesn't have, and it does it in an indirect way. But here, let's see if you can see it before I say it, and if not, that's fine too. It tells you that if you take the cross product of u and v, and you now instead take the cross product of v and u, so in other words, just swap their orders. So take the cross product of v and u. Well, if the cross product was a commutative operation, then this equation would be true, but unfortunately it's not. We have to put a negative sign out front. So really what this is telling us is that the u cross v and v cross u, they're not the same for starters. But the good news is they are relatable. So it is nice. If you want to switch the order of your cross product, you can do it. You just have to put a negative sign in front. That's the price you'll pay for switching the order of your factors in a cross product. So it's nice that you're able to do that. But the fact that these are not actually equal, the fact that we needed to put that negative sign there is what tells you right off the bat, among other things, that the cross product of vectors is not commutative. So it's not associative because of properties 4 and 5, and it's not commutative because of property 6. But it is distributive, and that's what properties 7 and 8 is going to tell us. So here's what that means. If I take the cross product of u with the sum, I messed this up. I want to make sure it's clear, so I'm going to just start this over an inch to the right, so I don't end up writing over myself. So the cross product of u with the sum of v and w. Well, so this means add the vectors v and w first, and then take the cross product of u with the result. Well, it turns out you can take the cross product of u with v, then take the cross product of u with w, and then add them afterwards. So you can distribute that u into the brackets. That's really what we mean when we say it has the distributive property. Or it distributes into addition. That's the language that other people would use too. So this is equal to u cross v plus u cross w. So it distributes into addition from the left. Now, because of property 6, and we know that the order of the vectors matters in a cross product, we can't immediately assume that this is that cross product will distribute into addition from the right as well. Although in this case it turns out it does, but that's actually going to be a separate property. It doesn't automatically follow from the seventh property. So property 8 says the following: if we have two vectors u and v and we add them, and then take the cross product of that with some third vector w, well, then this w vector will distribute in from the right as well. So that's what property 8 says. So I can go, this is equal to u cross w plus v cross w. That's what property 8 says. All right, property 9 tells us something about what we will get if we multiply a cross product by a scalar. So that's where this scalar k is going to come in now for property 9. So if you take a scalar k and multiply it by the cross product of two vectors u and v. So this is actually scalar multiplication onto a vector here, because this is a vector. Well, it turns out you can compute this in two other ways as well. You can take k and multiply it directly onto the vector u, and then take the cross product of ku with the vector v, or you can multiply the scalar directly onto the vector v and take its cross product with u, although you have to preserve the order. You can't change the order of u and v here. V has to stay on the right and u has to stay on the left, but these are three ways of computing the same thing. You can take the k, multiply it onto the u directly like we did here, or you can take it and multiply it directly onto the v like we did over here, and then take the cross products afterwards. Or you could just use what you have. You could just take the cross product of u and v first, then whatever the result is, multiply the scalar k on afterwards. But you have those three options. There's a really similar property like this for the dot product. If you go back and check the list of properties of dot product, you'll see that we had a similar property there. Property 10 tells you something. If you take the cross product of any vector u with the zero vector, what do you think you're going to get? Well, before I write that down, you might guess the zero vector, just because that seems to be what happens when you multiply something by 0. But before we make that guess, and I don't know if you made that guess or not, I kind of put the words in your mouth, but let's just think it through. Right? If the second vector in the cross product is the 0 vector, what would that mean for this definition? That would mean, take v to be the 0 vector. That would mean the bottom row of your determinant is equal to 0. So your determinant has a row of zeros. What do you know about matrices what do you know about the determinants of matrices who have a row of zeros or a column of zeros? Well, we know that their determinants are 0. Now that's not quite rigorous proof here, because remember, technically this isn't really a determinant, because the top row is actually vectors, not real numbers. But the same logic applies. It'll turn out that if you do have a row of zeros, if either u is the 0 vector or v is the 0 vector, then either your second row is equal to a row of zeros, or your third row is equal to a row of zeros. And in either case, you're going to end up getting 0 for the determinant. So that's what property 10 says. So the cross product of u and the 0 vector, or if I do it in the other order, if I take if I go u cross 0 or 0 cross u, in both cases, you just get the 0 vector back as the result. Okay, and then property 11 says that if you take the cross product of u with itself, well, that's one you can actually think about by going back to this definition as well, or this formula, I should say. What if u and v were the same vector? Well, that would mean that the second and third rows of this determinant are the same. And if you remember back to section 2.3, I think it was, if you have a determinant where one of the rows is a multiple of the other, you can automatically conclude that the determinant is 0. So that's powerful. So in the case where the second and third rows are equal, that would certainly fall into that case. And again, this isn't technically a determinant, so that's not really a formal proof, but it ends up working, and it works for exactly that reason. If you have two rows that are equal, you're going to have a 0 determinant. So if u and v are both equal, you're going to have a 0 determinant, and hence the cross product is going to be 0. So the cross product of any vector with itself is the 0 vector. That's the important point here. Okay, so those are some properties of the cross product that we have access to. But what we haven't done a lot of is actually working with calculating cross products. We've done one example, but we haven't done anything beyond that. So that's what this next example is going to be. And it says, compute the cross product of each pair of standard basis vectors for R3. So that's actually quite a few cross products here. But it turns out we don't have to do them all from scratch. But let's do one. Let's do the first one from scratch, at least. So here's how we'll start this. So the first cross product that you might consider is I cross I. Okay, the cross product of the I with itself. Right, and just for reference, we've already said this before. Maybe I'll just sneak it in here. Remember that I is the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1. Just a reminder, right? I, J, and K are the standard basis vectors that we need those to use our memory trick for the cross product in order to use this formula here, because you need to know what those top three vectors are, right? Okay, so let's compute the cross product of I with itself. Well, that one we actually don't need to compute, because property 11 says the cross product of any vector with itself gives us the 0 vector. So this one we get for free. That's just going to be the 0 vector. Okay, well, let's do another possibility. There's actually going to be 9 in total, because there's 2 factors and they each have 3 possibilities. So 3 times 3 is 9. That's how you know there's going to be that's how you know there's going to be 9 possibilities. So the next one we're going to look at is I cross J. So let's work this one out from scratch. So let's take the cross product of I and J. So what do we get if we do that? So, well, it's going to be the determinant of this 3 by 3 matrix. The top row is going to be I, J, and K, right? And the second row is going to be the coordinates of this first factor, which are 1, 0, and 0 here. So the second row is going to be 1, 0, 0. And then the second factor here, the vector J, its coordinates 0, 1, 0, those are going to be the third row. And then the rest is just working out the determinant by a cofactor expansion along the first row. So if we do that, our first term, we're going to have the vector I multiplied by the determinant of this 2 by 2 matrix, which is going to be 0 times 0 minus 0 times 1. So this product is 0, and this product is 0 as well. 0 times 1 is 0. So really you just get 0 minus 0. So that's the first term. So now the second term will switch signs. It'll be negative now because we're moving on to J. And we're going to have J times the determinant of the 2 by 2 matrix formed by looking at these 2 entries and these 2 entries, right? Because we're going to delete the row and column occupied by the vector J. So we have 1 times 0 minus 0 times 0, which again, that's just going to be 0 minus 0, which is 0. And then for our last term, we'll have plus K, because that's the third entry in this row. So we'll have K times the determinant of this 2 by 2 matrix. And this is the 2 by 2 identity matrix. So we know that its determinant is equal to 1. Or you can just compute it from scratch. 1 times 1 minus 0 times 0. So that's going to be 1 minus 0, which is just 1. So this is multiplied by 0. This is multiplied by 0. Really, this is scalar multiplication. I've just written the scalar afterwards. Usually you don't do that, right? Usually if you're doing scalar multiplication, you'll write the scalar in front, like I did here, right? K times U, or K times V, or K times U cross V. Usually you don't write the vector first and then the scalar afterwards. So why am I doing that? Just because that's just ends up being the way that's the order in which you think of things if you're doing cofactor expansion along the first row here. But really, this is just scalar multiplication. This is 0 times the vector I, 0 times the vector J, and 1 times the vector K. So these are just going to be the 0 vectors, but you add on a copy of K afterwards, so you end up getting K. Okay, so really now what we get is I cross J is equal to K. Okay, now I didn't leave myself a ton of room. I wish I would have done this a bit lower actually in hindsight, but I wanted to do 9 cross products in total, so I want to squeeze the other one in here, and then we'll do 3 here, and then we'll do 3 here, and then I'm going to draw a diagram here that actually helps you remember how this works a bit more. because the next one would be I cross k, right? Taking the cross product of I with k. And then that would be all your three options that have I for your first factor. So to work this one out, what would you have to do? Well, technically you just have to repeat these calculations, except for the third row, instead of using the vector j's coordinates, you'd use the vector k's coordinates. So you'd have 0, 0, 1 as your third row, and then you'd repeat these calculations. But I'm actually going to show you a shortcut here. There's another trick you can use, a memory trick, for taking the cross products of standard basis vectors. And it's really easy. Just draw a circle and imagine it like a clock, in the sense that you imagine motion going around this circle by default in a clockwise fashion. Then draw the vector I on the top, then draw the vector j down here, and then draw the vector k over here. So this is a bit sloppy. I want to fix that. So you got the vector j down here. All right, so that's your circle, and you draw those three vectors, and here's how you can do the product, right? If you want to take the cross product of any two vectors, like I and k here, for example, the result is just going to be the other vector. So, but if it's I cross k, so start at I and move to k next, and then you're going to get your answer over here. Except, ask yourself, if I go from I to k, I'm actually going against this clockwise motion. So if you're going counterclockwise, then your answer is this vector, but with a negative sign. But if you go in the clockwise direction, so for example, I cross j was k, right? So if I go I cross k, if I go I cross j, I get k, because I'm going in the clockwise direction. But if I go I cross k, I get negative j, because I'm going in the counterclockwise direction. That's how you can fill them all in. And that's just one example. We'll do the rest as well, just to clarify. So that's what you're going to get. You're going to get the vector j here. And just to maybe remove any possible confusion here, I want to just draw a line to split those up, so that work gets separated. Okay, so we've got 6 more products to finish this example, and that will give us a chance to really practice using this diagram. So let's do the 3 cross products with j as the first factor. So we got j cross j, j cross k, and j cross I, in no particular order, really. Those are the 3 products we can do with j as the left factor. So j cross j, well, you can do that one with this property 11 right here. Anything crossed with itself is the 0 vector. So you don't need the diagram if both of your factors are the same. And in fact, that's good, because the diagram wouldn't help you in that case. But for j cross k, well, start with j and go to k. So start with j and go to k. That's clockwise, right? So the answer is just going to be the next vector, I. So j cross k is I. But j cross I, so start at j and go to I, well, that's counterclockwise. Right now we're going against the arrow's direction. We're going j cross I, so we're not going to just say k, we're going to say negative k. So the result here is going to be negative k. Right, so those are all the products with j as the first factor. Then there's 3 more products, and they all have k as the first factor. So we'll have k cross I, k cross j, and k cross k. And k cross k, right, that's, again, going to fall under property 11. Any vector crossed with itself gives you the 0 vector. And then if we take the cross product of k and I, so k cross I is going to be j, because we went clockwise around the circle. So we're going to get j for that one. And then k cross j, that's counterclockwise, so we're going to take negative I. Okay, so this diagram really has all the cross products of the standard basis vectors wrapped up into it. Of course, you can work them out from scratch. If you don't like this diagram, I mean, it'll save you a lot of time, but if you don't like it, you can always just do them from scratch each time. Okay, so that's how you can work out the cross products of standard basis vectors using this diagram. But now, coming from this, we're actually in a position we can add one more thing up here. Remember when I said in general that the cross product's not associative? And in particular, what I really meant by that was that this expression over here in general is not equal to this expression over here. So if they're not, the left and right hand sides of this non-equality are not in general going to be the same. Well, why don't we come up with an example? And actually we're in a position to do that. So for example, just take u equal to the vector I, and then take v and w both equal to the vector j. So let's go I cross j cross j. Well, what would that be? Well, on the right, these brackets would tell you that you have to compute this cross product first. So the cross product of j with j gives us the 0 vector. So this is really I crossed with the 0 vector. And property 10 says that any vector crossed with the 0 vector just gives you the 0 vector. So we end up getting the 0 vector. But what if we computed the cross product of the same vectors, but we changed the brackets? So it was I cross j first, and then the result is crossed with j. What if we did the brackets like that? Well, then you would do this product first. I cross j, and that's down here. I cross j gives you k. So really, this is k cross j, right? And k cross j we can get from the table down here, or from table. We just worked them all out, so we can just take it from here, but you could just use the memory trick to do it. But k cross j, all over the place here, is down here, right? K cross j is negative I. So with the brackets around the two j's, we get the 0 vector, but if the brackets are here, we get negative I, which is not the same. So therefore, really the important part here is that I cross j is not the same as I cross j first and then take the cross product with j. So that's the important part of this example. And I'm going to just draw a line here to separate this so it's a little easier to pick out what's happening. So yeah, I'll leave it at that. So that is, that gives you a lot on that page actually. Now, the next page, what we're going to look at is the orientation and length of the cross product.